Welcome to a new chapter in Machine Dynamics 2, a chapter that deals with belt drives. So belt drives, they have several advantages. They are very inexpensive, they are simple, they are very flexible, and of course they are shock and vibration absorbing. So they are rather noise-free because there are no gears or no wheels that contact, and all the contact is done by a belt. And that belt is usually an elastomer or something similar, so with very good shock and vibration absorption properties. So that's very good. However, there might be one disadvantage, and we want to study this disadvantage, namely such a belt may vibrate, especially there will be transverse vibrations. And therefore in this chapter we study transverse vibrations of belt drives. So the key question then is, how does the velocity of the belt influences these transverse vibrations? So similar to the rotational speed in rotors that might lead to resonance or not, there might be an influence here of the belt velocity on these transverse vibrations. And what we will see is that the belt velocity tunes, that is, changes the natural frequency of these transverse vibrations. But in order to study this, we have first to derive the equations of motion. We will see that the influence of the belt velocity, by the way, the influence of the belt velocity will be seen in the inertia part, that the influence of the belt velocity already changes or has an influence on the equations of motion on the, let's say, on the left-hand side, on the system part, due to the inertia terms. And then we will solve in this video the equation that describes the transverse vibrations, but only for the case that the belt velocity is zero. The case that the belt velocity is non-zero will be treated in another video, in the next video in this session for this chapter. There are two videos. Okay, so what are these transverse vibrations? Well, what we will see that is that there are two sources for these transverse vibrations. The first one are string vibrations, due to the fact that there must be a certain force, pre-stress on that belt, otherwise there would be some kind of slip at the wheels. And the second mechanism is, of course, bending vibrations. So we will study the joint, string and bending vibrations for the belt at rest. But first of all, we derive the equations of motion, and these equations of motion will be derived in a general way, that is taking the belt velocity into account. So let's start again with the derivation of the equations of motion, and for this we study again such a small volume element of that belt. It's similar to a bending beam element. You have that element. It will have a length of delta x here. On the left-hand side, the reaction forces and the reaction torque are marked as F in normal direction, Q in transverse direction, mm is the bending moment. On the other side, all these quantities are then changed a little bit by some influence delta m. So we have m plus delta m, q plus delta q, f plus delta f, and also the angle here. The curvature is changed to alpha plus delta alpha for that element. If you look at that coordinate system, the x direction points to the right, the z direction and also the displacement in z direction, the transverse displacement or w, points downwards. And we will study this plane, well, bending and a vibration problem just in one direction, in the W direction of the belt. Okay, so this would be nearly everything. There is another force. It's the inertia force. As you can see, as we are studying only the z direction, there's only one in opposite to the transverse direction, one inertia force. And the inertia force is composed by the mass, well, a product of the mass density and the cross-section area mu, the length delta x, so that we have the mass of that tiny little volume element. And then we multiply by the second derivative of a displacement w with respect to time. And already here you can see that I used a little bit strange notation for that second derivative. It's a capital D. Why? Because that derivative, the acceleration, is taken by following a particle on the belt that moves. That is, we take here the so-called material acceleration or the material velocity, and from that the material acceleration by following a moving particle. But first of all, let's formulate the balance of forces in transverse direction. So we have q plus delta q with the angle cosine alpha plus delta alpha, so this angle here. And for the sine term, we have f plus delta f, and the sine alpha plus delta alpha. As you can see, the normal force points opposite to the z direction. Q plus delta q points in z direction, so this term carries a positive sign, this term carries a negative sign, and on the opposite side, on the left hand side, we have then opposite signs, so it's q cosine alpha that points opposite to the z-axis, and the projection f sine alpha that points now in z direction, and the transverse inertia force points opposite to the transverse direction. So in the sense of D'Alembert, we would have minus mu delta x second derivative of w with respect to time. Now, as I said, this second order derivative here, the acceleration, is the material derivative. So it's not the simple partial derivative with respect to time. Sometimes this is also called the substantial derivative. Yeah? So with respect to substance, but I think a better way is to say it's a material time derivative because it's for a fixed material point on the belt. So if we look at our little volume, then as the belt moves, our little volume element would move with the belt, and therefore we have to take the material time derivative here. The material time derivative is composed by the partial time derivative plus the velocity of the belt times dv by dx, because we're considering only the x direction here. So motion of the belt in x in longitudinal direction. For the second derivative, we then have to take the material derivative of the material derivative, leading to a second order derivative, partial derivative with respect to time, twice the term v of t, and the derivative, a mixed derivative of the displacement with respect to x and t. Then we have the term v squared and the second derivative of v, partial derivative with respect to x. And then, as v can be time dependent, something we will not consider anymore in these videos, we will always assume a constant belt velocity. But if the belt velocity is non-constant, you would have this term here. So the derivative of the velocity of the belt with respect to time times dv by dx. Okay. The notation for this is, to be a little bit brief, where we put these derivatives as indices, so as subscripts of the appropriate letters, so either the displacements, and for the belt velocity I just put a dot here. But as I said, this term will not play any role. We will assume constant belt velocities always in this chapter. So for a constant belt velocity, the equation then simplifies to having the first term, the second one, and the third one, and that constant belt velocity is always denoted by a V naught. Okay, we can insert this result into our equation of motion, but we have to further substitute also the reaction forces that are included in our equation of motion. So let me come back to that equation of motion. So we have clarified the last term, the inertial term, already on the previous slide, and now we look at these terms here at these reaction forces, normal and shear forces, and also we have to specify the angle here. So for a small angle alpha, we set the cosine of alpha equal to 1. The sine alpha will then be equal to the tangent alpha, and here you have to pay attention. It's now minus wx. Why is this the case? Because our w-axis points downwards. Yeah? And if you look at the definition of that angle alpha, then the tangent of alpha is equal to minus wx. It's not wx itself, it's a negative sign, yeah? Due to the choice of the coordinate system and the angle alpha. So if we insert this and then we divide by delta x, and then we take a limit of delta x to 0, what do we obtain? Well, if you look at the first two terms, where you insert here the cosine alpha to 1, so then you have the delta q, because you have q plus delta q minus q, so delta q left. If you then divide by that delta x here, then you would have delta q by delta x, and you take a limit value, then you have q with respect to x. Yeah? So, last equation, sorry, forgot. Sine alpha plus delta alpha is replaced by tangent alpha plus delta alpha minus wx minus delta wx. So now here comes the first term, qx. Second term is a little bit more difficult to see, perhaps. You have f plus delta f, which you multiply by, so the negative sign here goes away. You get a positive sign, wx plus delta wx. If you do this, then you will find first zero order term, f wx, first order terms that include 1 delta, f delta wx, and delta f wx. And you will find a second order term, and that second order term is neglected in the same sense we linearized here. So the term delta f times delta wx will be neglected. On the other hand, you have f times wx, so the zero order term will cancel with the f wx here. Yeah, this one will then be positive, this one will be negative. The remaining terms are then an f a delta wx and a delta f wx. And if you divide by a delta x and take the limit value, then according to the differential calculus, you arrive at f x wx plus f wxx. And by the product rule, this can be simplified to be fwx, and then you take from the whole term the derivative with respect to x. And for the last term, you just divide by delta x, so this term will be independent on delta x, and also the limit value will then be clear. It will be just minus mu second material derivative of w with respect to time. So this will be the equation of motion in a simplified way, and now we have to find expressions for q and for, well, for f we leave f to be the longitudinal force, but for q, for the transverse force, and we have to relate that transverse force to the displacement w to find an equation that contains the displacement as independent variable or as variable only. Yeah? So for the for the transverse force, we relate it to the bending moment. Mx is equal to q, and for m we have the equation of the bending line, so minus E times I, the bending stiffness, and the second derivative of W with respect to X, with respect to space. So in total we have a third derivative here, the derivative of q, and a fourth one here, the derivative of q with respect to x. So we arrive at EIWXX, and then we take the second derivative. The sign would be negative, so I multiply everything by -1. Therefore, this sign is then switched to a -1, and the last one for the inertial term is then a positive one. And this would be the equation of motion. And now if you insert for D the expression for the material time derivative, you would have the equation of motion for the moving belt. Yeah? So that is summarized on the next slide. The differential equation, a partial differential equation for the transverse vibrations of that moving belt is simply here. The bending stiffness times Wxx, and then you take the second derivative again, and minus the longitudinal force Fwx, and you take again the derivative with respect to x, plus the inertial term mu second material derivative of W with respect to time, and this is equal to 0. I would like to insert here the material time derivative, but only for the case of a constant belt velocity, and just to show you what you would get there. So you would have EIWXX, and then the second derivative with respect to x, minus Fwxx. If we assume that F, the longitudinal force, is constant, so like a pre-stress that acts once on these wheels, and then the belt is stressed in longitudinal direction. And then we have mu Wtt plus 2V0 mu Wxt and plus mu V0 squared Wxx. This would be the partial differential equation. In order to get a unique solution, we have to apply boundary and initial condition. So this is a problem that needs boundary and initial conditions. We have time derivatives here, and we have derivatives with respect to our space variables. No? As with respect to space, we have fourth order derivatives. We need 4 boundary conditions, well, with respect to space, so boundary conditions. And as we have the second order time derivative, we need 2 initial conditions. So let's start with the boundary conditions. Well, for the moment, what we will assume is that the wheels are transversely, or the belt at the wheels is transversely rigid. So no displacement at x equals 0 and x equals L at the starting point at one wheel, so where the belt leaves the wheel, and at the reattachment point at the other wheel at x equals L, the transverse displacements should be 0. And then that connection should be torque-free, so the second order derivative with respect to x at the same place should be also 0. And for the initial condition, we have to prescribe the shape, so the displacement of the belt for the whole belt at time t equals 0. And not only the displacement we have to prescribe, but also the initial velocity for every point of the belt. Yeah? So here you can see that. So for time t equal to 0, you could take, of course, t equal to t0 or some other point as well. You have for any point x, you need a function fx and another function g of x for the velocity, yeah? For the derivative, partial derivative of w with respect to time. Okay, so with this, the problem is fully specified. So let's solve it, right? But we will first solve, as I said in that video, we will solve the easy case, the case where the belt velocity is equal to 0. So where these terms vanish, and we have a partial differential equation that combines bending and string vibrations here. This serves as a nice repetition of what you learned in engineering mechanics 4 at the very end, when we talked about vibration theory, what you learned about continuum vibrations. So let's follow this approach step by step. We consider the belt at rest. we consider a constant bending stiffness, a constant preload force F. So the equation of motion is then simplified a little bit more. It's EI, the bending stiffness, W, and force derivative with respect to x, minus F, W, second derivative with respect to x, plus mu, W, tt. All the terms are well separated. The derivative with respect to time sit in one term. The derivatives with respect to space sit in the other two terms. So therefore we can solve, and it's a linear equation of motion, therefore we can solve this partial differential equation by applying Bernoulli separation. Bernoulli separation, well, splits our displacement field that we are looking for into the product of two functions, one function that governs the space dependence and the other function that governs the time dependence. By the way, if you want to solve such equations numerically, you do more or less the same, but not with one term, but with several terms that you add. It would be kind of superposition principle. Of course, superposition principle would only be allowed for linear equations. You could apply such an approximation with several terms, also for nonlinear equations. But the idea is the same. It's that you split and then each function governs one variable. The good thing is that then you will, at least you will strive for it, you will get ordinary differential equations for these functions w and theta. So how do we get these ordinary differential equations? First of all, we insert this setting into the equation of motion. And then we write all the terms in w on the one side and all the terms with theta, so therefore separation, on the other side of an equation, so of the balance, I would say. Yeah. Okay, so this is done here. Let's just check this. So here we take the fourth derivative of w, which is here, and the second derivative with respect to f, and then we had to multiply by theta. We put this term on the other side, therefore the sign changes to a negative one and to a positive one, and we divide by theta to get rid of that theta with which we multiply this term. Yeah? Therefore the theta will then appear in the denominator of the other side. There's just one term left, this one here, the inertial term. Well, if you insert the setting here, then you get twice the derivative with respect to time. Here it is. And now you have to divide by w to get rid of the term w that is space dependent. So you multiply, you divide by mu times w, and it appears then in the denominator of the left-hand side. So with this, the left-hand side is completely space dependent, while the right-hand side is completely time dependent. And therefore these expressions must be constant. Well, let me explain this once again. Why should they be constant? If you have one part of an equation that is space dependent, the other part that is time dependent, you can conclude that these terms have to be constant. Why? Because you can change time and space independently. They are independent variables. This can be very well imagined. Suppose that motion of that belt is like a video. Now you could stop that video at one position, that is, you fix the time, and then you get one image of that beam. And you look at that image and you will say, oh, belt. No? You would say, oh, what a nice belt. It has such a nice displacement. And you know, when you are talking about this displacement, they can be different from space position to space position. Therefore, theoretically at least, the left-hand side, which carries these space dependencies of the displacements, could be different. Could be, because the right-hand side isn't. Because if you fix the time, if you just take out one image of this video, then the right-hand side is fixed. You stop the time at a certain time t equal tau, so the right-hand side will be fixed to the second derivative of theta with respect or at time tau divided by theta at time tau. And as the right-hand side is fixed and there is an equality sign here, the left-hand side must be fixed, must be constant as well. Now you can argue the same way if you just let the video move, so the time is now running, but you are fixing somehow with the laser pointer, perhaps you are fixing one point of that belt. So the left-hand side will be fixed. You are fixing that point x. Time t is running. So theoretically, the second derivative and theta are allowed to change, but if you look at that ratio, the second derivative of theta divided by theta, you can be sure that this must be a constant because the left-hand side does not change. Because you fixed with your laser pointer or magic instrument, you fixed that point x, and therefore you fix the value of the function w and also its derivatives. So the left-hand side is not allowed to change. It's an equation, so therefore the right-hand side is not allowed to change as well. So we deduce from this, by just logical arguments, that these ratios must be constants. Now let's give this constant a name. We don't know its value, but we give it a nice name. That name chosen here appears for you perhaps a little bit strange at the very beginning. I called it minus omega squared. But if you have a closer look at that equation, you can see why I put minus omega squared here. Because the right-hand equation that I would obtain by multiplying everything by theta would be theta double dot is equal to minus omega squared theta. Putting it on the left-hand side, I would arrive at theta double dot plus omega squared theta is equal to 0. And you know that equation quite well from engineering mechanics. It's the equation for the free undamped vibrations of a single degree of freedom oscillator, and then omega is the natural frequency. So we already know the time dependence. So that function theta, it's a harmonic function. So it's a composition of a cosine and a sine function, and there will be two integration constants, everything the same as for free undamped vibrations of a single degree of freedom oscillator. You might ask at that point, why do you put minus omega squared here? You would say, okay, I understand, then you get the nice single degree of freedom oscillator. But why and how do you know that you can exclude positive values here for that constant? Why do you know that that constant is negative? Well, I have to admit that if you just look at these equations, you won't know. No? But you can be sure if you put a positive sign here that you run into trouble to satisfy the boundary conditions. No? And well, you can do all these computations, just put a positive sign here and then follow the computations that will come with the negative sign and convince yourself that there is no solution if you put a positive sign there. Yeah? But I wanted to protect you, I could say, from doing computations and then at the very end seeing that there is no solution. That's a little bit disappointing. Therefore, I just took the correct sign here at that place. But you can leave that sign for a moment if you want. You can leave it open and you can check that a positive sign here, a positive value for that constant, does not lead to any solution at all. So let me summarize. By putting here, first observing that it is a constant, and by putting that constant to minus omega squared, we arrive at the following two ordinary differential equations. The first one is the classical vibration equation for free undamped vibrations of single degree of freedom oscillators. The second one looks a little bit more complicated. It's well, for the first one we have the classical harmonic solution, and the second one looks a little bit more complicated. It's bending stiffness times fourth order derivative minus f w double prime. So I changed again the sign here. Then we would have a negative sign. We put it on the left hand side, get a positive sign. We multiply it by minus 1. We get again a negative sign of minus mu omega squared w. And this is a time independent because it just depends on x, ordinary differential equation. So the ordinary differential equation that governs the space behavior of the solution of these displacements. And it's again a homogeneous equation, but it's now a boundary value problem. We prescribe conditions at both ends, at both boundaries. This is the difference. And now let's solve the second equation. The second equation is a boundary value problem with one parameter, omega, because we do not know that omega. We do not know that natural frequency of these free undamped vibrations until now. And we can't hope to determine it from that equation. Well, have you ever seen a free undamped vibrations where you compute, where you see the solution and you compute that omega? You would get it from the system parameters. But here, omega does not come from any system parameters. It's at the moment a free parameter, and if you have a boundary value problem that contains that free parameter, then this leads to an eigenvalue problem when you try to satisfy the boundary conditions. So let's have a look at this eigenvalue problem on the next slide. So this would be the equation for capital W. The boundary conditions that govern capital W have to be derived from the boundary conditions of the displacements, where these were no displacement conditions, so therefore we set capital W to 0 at both ends, and it were torque-free conditions, so the second derivative with respect to the space variable of the displacement field W is equal to 0, therefore we put the second derivative of that function capital W from Bernoulli separation also to 0. Now the following is a general approach, and we will follow that approach several times here in the remaining videos, how to obtain and how to solve such an eigenvalue problem. First, we need the solution of the ordinary differential equation. For this, as we observed that this a linear ordinary differential equation, we use our classical exponential ansatz here. So our setting with an exponential function and with some unknown lambda. When you insert this, then you see that you get lambda in fourth power here minus lambda in second power minus a term that is independent of lambda. So lambda appears in fourth and at second power. Therefore, it makes sense to abbreviate lambda squared by some other quantity, chi here. I know there are better letters in the Greek alphabet than a chi. And then we obtain a second order polynomial for chi. The solution for that second order polynomial are, well known to you in school, the famous Mitternacht formula or midnight formula, I would call it. Chi1 is equal to f minus the square root of f squared plus 4e times I, the bending stiffness mu omega squared divided by 2ei. And the other one would be f plus that square root of s squared plus 4ei mu omega squared divided by 2ei. And I know that these two solutions are real valued and of opposite sign. Why? Well, if you look at the radicand here, then you can see that it reproduces the f here, the first term. And for the second, I can be sure that it is something positive, because E is positive, Young's modulus, I is positive, second moment of area, mu is positive, it's the product of mass density times A, and omega square, of course, is also positive. So everything is positive, so you add something to that f squared. So if you take the radicand, you get something that is larger than f. Well, if you deduce something from f and it's larger than f, then it must be negative. So the numerator is negative. For the denominator, you know for sure that the bending stiffness is positive, so the term must be negative. Of course, here everything is positive, so you divide by 2ei, so you get something that is positive. This is the result for chi. Now we have to take the square root because we did our exponential setting with lambda. Well, for a negative value here, you get a purely imaginary conjugate complex pair. So you get something that has only an imaginary part with a positive and a negative sign. That's not unusual. That would be the classical solution you would also obtain for a single degree of freedom oscillator with such an exponential setting. Of course, you would have in that case only second order derivatives, but you would get something that is purely imaginary, and you always get the complex conjugate pair. You know that this leads to a harmonic term, so to a cosine and a sine harmonic term, to harmonic oscillations. But be careful, here we are not going to talk about some kind of oscillations or some kind of time behavior. We are looking at space behavior and at a boundary value problem. Therefore, also the other term makes sense, or could make sense at least. You see, it has a positive sign. That is, chi is positive. You can take the square root. You get something that is real, either a positive or a negative real constant. For time-dependent behavior, you would say, alert, alert, alert. In my general solution, I found a term that has a positive real part, an exponential with a positive real part. For time-dependent behavior, that wouldn't be possible. Because for time-dependent, that means you have a part of your solution that increases exponentially in time. But here we are looking at space behavior. That space behavior is limited to a range of x between 0 and L. Why shouldn't there be a positive exponential between 0 and L? You normalize perhaps the L, you divide by L to set the interval to 0 to 1. So why shouldn't you have a nice exponential with a positive argument between 0 and 1? No problem with that. Yeah? Only when it comes to asymptotic behavior. So if your structure would extend to infinity, well, like the Tower of Babylon, which crashed, I don't know, that wouldn't work. Yeah? So, but for the moment, we can accept all these terms, and we have to accept, of course, as parts of the general solution. So this leads to classical exponential functions, and they can be also summarized, but not in sine and cosine harmonic, but in hyperbolic sine and hyperbolic cosine functions, so that we get as a general solution 4 functions, a composition of 4 functions, a sine harmonic with respect to lambda 1 refers to chi 1, cosine harmonic refers with respect to lambda 1, so refers, as you can see, to the square root of minus chi 1, because chi is negative, so the imaginary unit is already taken account by Euler's formula in the sine and cosine functions, and hyperbolic sine and hyperbolic cosine function with respect to that value lambda 2. That would be the general solution. Now we have to adapt the general solution to our boundary conditions. And let's see how that works. So this would be the second step. We solved our our ordinary differential equation. We get to the general solution, and in a second step, we adapt that general solution to the boundary conditions. Let's start with the left boundary condition. That's always easier to plug in a 0 in that equation than a value L. So W at 0 is equal to A2, the cosine is 1, and the cosine, hyperbolic cosine is also 1, and plus A4, and the other terms will vanish. So we get A4 must be equal to minus A2. We take the second order derivative. So then the cosine reproduces itself after twice derivating, but with a negative sign. And of course, by taking the inner derivative into account, minus lambda 1 squared A2 plus lambda 2 squared A4. Now let's insert the result here. Then you would have, I would say, an alternative, either lambda squared plus lambda 1 squared plus lambda 2 squared is equal to 0, or A2 has been equal to 0, and then if A2 is equal to 0, then also A4 has to be equal to 0. Is it possible to have lambda 1 squared plus lambda 2 squared equal to 0? If you just think briefly at the solution of that quadratic equation, then you will immediately say, no, it's not so possible. I will show you. So lambda 1 squared plus lambda 2 squared is minus chi 1 plus chi 2. And this is equal to that square root that we had. So the term that changes sign when we consider the two solutions of the quadratic equation, or the term that changes sign in the famous midnight formula. F squared plus 4ei mu omega squared divided by ei. Everything is positive, so the only way to get this term to 0 is you have no force and you have no bending stiffness, or no mass, I don't know. That's impossible. So it's not possible that lambda 1 squared plus lambda 2 squared is equal to 0. So a2 and a4 must be equal to 0, and this switches off already two terms in that general solution. So we just have to deal with the first and the third term for now and for the right boundary. So simplifies the things for the right boundary. Now we plug in x equal to L, and we have a1 sine lambda 1L plus a3 sine lambda hyperbolic sine lambda 2L is equal to 0. And for the second equation, taking the second derivative, again the sine function reproduces itself with a negative sign and with an inner derivative lambda 1 squared, and the sine harmonic reproduces itself with the inner derivative lambda 2 squared. Now, of course, one way to set this term to 0 is, well, first of all, observe that we have to set a3 to 0, because we could multiply that equation by lambda 1 squared, then add the two equations. The first term is of opposite sign, the last term would lead a3 lambda 1 plus squared plus lambda 2 squared sine hyperbolic sine of lambda 2L must be equal to 0. As the sine hyperbolic sine function is just 0 for the argument being 0, we have no hope that this term is 0. We have no hope that the factor lambda 1 squared plus lambda 2 squared is equal to 0. So the only possibility here is that a3 is equal to 0. So we switch off the last but one term. The term was a sub 3. So our general solution now contains just of one term. And now if you switch off a1, which would be easily possible, because you have then satisfied these two equations here, you would have a very boring solution for that displacement, and a solution that would perhaps not match the initial conditions, namely there's no displacement. Wx would be equal to 0. This would be the trivial solution. That would be the solution we do not want to have. So the only way then to deal with that problem is the alternative. The sine of lambda 1L has to be equal to 0. So let me summarize. So by adding these two equations, we deduce that a sub 3 is equal to 0. And then non-trivial solutions are only possible if the sine of lambda 1L is equal to 0, so vanishes. This allows a sub 1 to take an arbitrary value, and a value we have to fix later on. So these non-trivial solutions are then solutions of a, well, eigenvalue or characteristic problem, one should say. I avoid to talk about a characteristic polynomial here because the sine function is not a polynomial. So you will get, as you can see, you will not get one eigenvalue, but what you will get from that condition is clearly a transcendent equation, and the condition that you get is you get countably infinitely many, because n is a natural number here, of these values for lambda. Pi times n divided by L would be possible values, possible non-trivial solutions, lambda 1n. And this fixes the eigenvalues. The corresponding displacements are called the mode shapes. So to each of these eigenvalues belongs a mode shape. So the pair eigenvalue and eigenfunction, or mode shape, is then called the mode, vibration mode of that continuum. And you see that these eigenfunctions are then the sine harmonic functions. You see that this sine harmonic function changes, so it could have, it could just be one, say one bow, and then you could have several bows depending on the number n, a natural number of n. Yeah? And then there is a constant to be determined. Yeah? Well, the lambda n's are not yet, they would be the eigenvalues of that problem, but they would not yet be the natural frequencies or something like this, because lambda 1n, well, is a quantity that has been introduced for the exponential function for that setting. It has nothing to do or it is not yet related to our omega before. Let's do this. Let's relate the lambda to the omega, to the constant we introduced after application of the Bernoulli separation theorem. That famous constant where I said it must be minus omega squared. That can be called a natural frequency because that omega governs the time-dependent behavior. It is the natural frequency of the time-dependent behavior because we have seen that the ordinary differential equation that governs the time-dependent behavior is that of a single degree of freedom oscillator, and to which that natural frequency omega belongs. Well, from our setting, when we solved the ordinary differential equation by inserting lambda, we obtained E times I bending stiffness lambda in fourth power plus F lambda in second power minus mu omega squared is equal to 0. Now we insert these non-trivial solution. So everything gets an n here, also the omega. And then we solve for omega. So this equation relates the natural frequencies omega n squared to these eigenvalues lambda we computed from our transcendental equation, which was simply the vanishing of sine lambda 1L, leading to these non-trivial solutions. Yeah? Solving that equation for omega n is simple. It requires just putting mu omega n squared on one side. What can you see already here from these natural frequencies? You can see that they are composed by one term that relates to the bending stiffness. It's the first one here. And the second one relates to the preload of these wheels, to the preload or longitudinal force F. And you see that the power is quite different here of that term in pi divided by fourth power and then second power. We will discuss that equation in more detail at the very end. I would like to follow the solution steps here for the moment. So what we did, first we solved the equation, the boundary value problem, let's say the ordinary differential equation for the boundary value problem. We adapted the solution to the boundary condition that leads to a transcendental equation from which we deduce the eigenvalues. We relate the eigenvalues to the natural frequencies. Now we write down the complete solution, composed by these modes, which are then multiplied, the mode shapes, so the displacement shapes, by the time-dependent behavior. Here it is. Yeah? And the constants are then reduced a little bit. You know that from the time-dependent behavior, you get integration constants C1 and C2 for the cosine and sine term that have to be determined from the initial conditions. From the mode shapes, you would get another constant. It was called A1n. Now, if you multiply A1n by C1, you would get C1n. And if you multiply by C2, you would get C2n. Yeah? So we have two sets of integration constants, and there are countably infinitely many of these integration constants. You can see that you have here the different natural frequencies and the corresponding mode shapes. So everything is assembled, the mode shapes and the natural frequencies and their time-dependent behavior in the complete solution. So therefore you need the modes consisting of natural frequencies and mode shapes to describe the complete solution. Now we have to determine these two settings of integration constants. Fortunately, we have orthogonality conditions for the mode shapes for these sine functions. Namely, from Fourier theory, you know if you have that sine function with some value of n and you multiply with the same sine function but possibly another value of m, so therefore n, so therefore it's called m here, then you would get 0 if n is not equal to m. Therefore orthogonality. So with respect to, one could say, a dot product that is formed here in a vector space of functions. So you integrate between 0 and L, functions that are continuous on 0 and L. And if you then multiply these two sine functions, then they are orthogonal in the sense that their integral is equal to 0, if n is not equal to m. If n is equal to n, you obtain the sine squared of pi n divided by L times x, and you can solve that integral to yield L divided by 2. And now we apply this to our complete solution. For the initial condition, we have to set t equal to 0. So if you set t equal to 0, let's take the first initial condition for the displacement. You get the function w here of x and t equal to 0. This was set to a certain function f of x. On the right hand side, you would lose the sine term and you would just get the coefficients c1n. You determine these coefficients that appear inside that sum by multiplication of the left and the right hand side of the equation with a certain sine function Pm divided by L and x, and then you integrate on the left hand side and on the right hand side with respect to dx from 0 to L. On the left hand side you would get a kind of Fourier integral, namely the integral from 0 to L of that function f of x, which corresponds to vx t equal to 0, times the sine of Pm divided by Lx dx. On the right hand side, you can apply the orthogonality of the mode shapes to just cut out one mode shape, namely the mode shape where n is equal to m, for which you obtain L divided by 2. You put the L divided by 2 on the opposite side, on the left hand side, and so you have 2 divided by L. So here you can see again the boundary conditions, and that is the way to obtain the C1n. I see it's continued on the next slide, all what I explained on that slide already. So you apply these initial conditions, you multiply by the mode shapes, you integrate, you exploit the orthogonality, and you would obtain 0 from L fx sine pi m Lx dx, and the L divided by 2 is here still on the right hand side, on that side here. Again, the same for the second equation, where you retain then after taking the first derivative with respect to time, you retain c2n omega n. You multiply again with some mode shape, integrate from 0 to L dx. So on the left hand side, you would get the integral from 0 to L g of x sine pi m divided by Lx dx. On the right hand side, you would get omega m c2m L divided by 2 from the orthogonality condition. So these are just Fourier integrals that you have to solve, Fourier integrals of f and x and gx. So these integration constants, they just lead to a Fourier decomposition of the functions f of x and g of x on the interval between 0 and L. Now, with this, the problem is completely solved and all the steps have been done. So we solved the ordinary differential equation, we adapted it to the boundary condition, we wrote down the general solution, and finally we computed the initial condition from an orthogonality relationship. Now we want to interpret the natural frequencies. These here. And as I said, the first term belongs to an influence of the bending stiffness, or also bending, and the second one points to the preload force. Now one could ask, which effect is stronger? Which effect should I well, retain, and is there perhaps one effect, bending or preload, that can be neglected? So for the bending vibration part, we have n pi divided by L and second power square root of EI mu, if we take here, if we compute the square root of that expression. For the string vibration part, we have n pi divided by L square root of f divided by mu. So we can write omega n squared as being n pi divided by L squared f divided by mu, and then we have a function n squared pi squared EI divided by f times L squared plus 1. And this is the decisive factor here, the term in parentheses. And I would like to plot this term in parentheses, this factor, which is n squared pi squared epsilon squared plus 1. And this is shown here for the epsilon, which is then the ratio of bending stiffness to, well, the preload influence, which is f times L squared. And you can see that function that runs here from 0 to 0.5. Why? Only to 0.4. Why only to 0.4? Because usually that preload f is much, much larger than the bending stiffness. If the preload would be too low, then, as I said, there could be slip of the belt, and this is usually avoided, so there is a large preload. So usually we are in that range here. And for this range here, so very small values of epsilon, you can see that that function psi n is around 1. It then starts to increase, and the higher, of course, the natural number n of that natural frequency, so for the higher modes, the increase is more pronounced than for the lowest mode. Usually the lowest mode is the most interesting one. The first natural frequency is the most interesting one. It's that one with the strongest resonance. The higher modes are better damped than the lowest ones, and less pronounced. The amplitudes are much smaller in general. So therefore what we can conclude is, if we are in such a situation that the preload is large enough, there is no influence of the bending stiffness on the natural frequencies, and therefore when we now study the moving belt in the next video, then we will neglect the influence of bending, which is good because it leads to that fourth power here and to a fourth order derivative with respect to time. We will simplify the problem and include only the second order derivative and include only the preload term. So we assume that the preload effect is larger than the bending effect or the bending stiffness, and therefore we exclude bending stiffness in the following. And this situation will be analyzed in the next video for the belt at rest once again, and also for the moving belt. So thank you very much for your attention, and see you in the next video.